So we are going to start with this Hermite cubic spline, right? So first of all, I am going to draw the diagram of this Hermite cubic spline. So this is the curve. So this is the curve that we want to generate. To generate a curve, you need to have 2 points, this point and this point. And along with these points, there should be 2 tangents on these points. So I am going to draw 2 tangents, one and second one is this. Second one is this. 2 tangents. First tangent at first point, let us take the first point as P naught, where u is equal to 0. And the second point is P1, where u is equal to 1. Right? From P0 to P1, right? Then this is the tangent of this is P dash naught. And the tangent of this is P1 dash. So need to draw a Hermite cubic spline, you need to have 2 tangents and 2 control points. As it is having 2 points, the equation that is governing this particular equation, this curve, is of 3 order, right? Let us first write that equation. Pu is equal to sigma I is equal to 0 to 3, then Ci Ui, where 0 is less than or equal to u is less than or equal to 3 or 1, sorry, less than or equal to 1. The value of u can reach from 0 to 1 only, because the parametric curve is from u to u equal to 0 to 1, right? Then expanding this equation, putting equal to 0, putting c equal to 0, that equation becomes, or starting from 3, the maximum value is 3, starting from 3, c3 u3, putting c3 u3, here it is I, plus c2 u square, plus c1 u1 u raised to 1, plus c3 c2 c naught, right? Starting from I equal to 3, then I equal to 2, I equal to 1, I equal to 0. This will be the equation for third order equation. In this case, C is the polynomial, a coefficient, and U is the parameter. Now the above equation can be written as, we can write it like this. Pu can be written as, now I am going to write u cube, u square, u and 1. U cube, u square, u and 1 as, and if you multiply it with this matrix, that is C3, C2, C1 and C0. The formula for that is, you have to multiply this horizontally to this one. The equation becomes C3 U1, U2 C2, U C1 and C0, like this. Just to solve on matrix, if it is multiplying, it will be multiplied like this. This horizontal will get multiplied to this. U3 will be multiplied by C3, and U3 will be multiplied by C3, and U2 will be multiplied by C2, and U1 will be multiplied by C1, and 1 will be multiplied by C0. The equation will be again same. This equation is written in the form of matrix, right? So this is equation. Now in terms of x, y and u, this equation can be written as in terms of xu, it is 3x u cube plus c2x u square plus c1x u plus c naught. Just adding x along these terms. Similarly, for y naught, yu, writing this equation in terms of y, c 3y u cube plus c 2y u square plus c y u plus c naught. Similarly, z is in terms of z, c 3z u cube plus c2z u square plus cz u plus c naught. These are the equations in the form of x, y, and z. This particular equation in the form of x, y, and z. Now, to calculate the tangent of this equation, this is pu, the equation of this curve or this point, particular point. If you want to calculate the tangent, for that you have to calculate p dash u, that is equal to curly u by curly pu by curly u with respect to u. You have to differentiate this equation with respect to u, and this equation will become, if you differentiate this with respect to u, it will become c 3c g3 u square plus, if you differentiate this equation with respect to u, 3c3u square plus, now differentiating this equation, 2c2u and differentiating this plus c1. This is p dash of u. This is the tangent of p naught. Just wait a minute. So this is the tangent. Let me explain the whole process again. This is cubic spline, Hermite cubic spline. And this, you need to have two control points, that is P0 and P1. And you need to have two tangents, that is P dash naught and P1 dash. Right? These are the differential of this equation. Putting these values, you can calculate that. So this is the governing equation. This is cubic curve. So that curve is of order 3. Cubic curve means it is of order 3. So that is why I is equal to 0 to 3 we have put it everything. Then Ci ui is the governing equation of this. Then we have put the value of I equal to 3, then 2, then 1 and 0. This equation has generated. Now this equation can be written in the matrix form in this way. Now this is the matrix form of this equation, right? Then moving to this is the equation written in the form of x, y, and z. Then we have to calculate the tangents also. The tangent of a particular point, it is the differential of the original point. So we are taking the differential of this equation in terms of u with respect to u. This is the equation. If you differentiate with respect to u, it becomes 3c3u square, then 2c2u and c1u. Sorry, there will be no u. It is raised to power 1 minus 1 will become c1. There will be no c naught in this case. So this is the differential of this particular equation. Now we are having two equations, pu and p dash u, right? Now what is to be done is putting u equal to 0 and 1. Putting value u equal to 0 and 1. As our 2 points are u equal to 0 and u equal to 1. That's why we are putting u equal to 0 and u equal to 1 in these two equations. We are having 2 points and 2 tangents. So that means 2 points, P naught, the value of P naught, P0 and P1. Putting value of 0, putting the value of u equal to 0, the value you will get P naught. Similarly, putting the value of u equal to 1, you will get the value at this end. So now to calculate tangent P naught, P dash naught, you have to put again 0 over here in this equation and again 1 in this equation. So there will be 4 points in this case. Now let us put u equal to 0 in this equation. Now P naught will become, if you put u equal to 0, this will become 0. This will become 0. This will become 0. And this is equal to C naught. You can calculate from this that P naught is equal to C naught. When you put P equal to 0, that means P equal to 0, U equal to 0. At this end, your value of P naught is equal to C naught. Right? P naught is equal to C naught. Then putting the value 1 in this equation, P1 will become, putting u equal to 1, this is C3, then C2, then C1 and C0. That means in this case P1 is equal to C3 plus C2 plus C1 plus C0 in this case, right? Similarly, you have to put the value of u equal to 0 in this equation and u equal to 1 in this equation. Now P dash 0, this is P dash u, putting equal to 0. Now this equation will become, if you put u equal to 0, this will become 0. If you put u equal to 0, this will also become 0 plus C1. Now you can find this P naught 1, 0 is C1. And similarly, now putting equal to 1, P dash 1 is equal to, now putting it equal to 0, no, sorry, 1, it will become 3, C3, putting it equal to 1 plus twice of C2 plus C1. Right? So this is the equation that will going to be generated. Putting equal to 0, putting equal to 1, putting equal to 0, and putting equal to 1. In case of points, in case of tangent. This is the equation for tangent, and this is the equation for points, two control points. So calculating these values, you will find out that I'm going to raise this portion. Calculating these values, C naught is equal to P naught. That is already calculated. C naught is equal to P naught. And C1 is equal to P dash naught. And similarly, C2 can be calculated. That is equal to 3 P1 minus P naught minus twice of P naught dash minus P1. Yes. And C3, the value of C3 will be twice of P naught minus P1 plus P naught dash plus P1 dash. you can find the value of C0, C1, C2, and C3. If you calculate, or if you want to you are going to solve these equations, you can find the value of C0, C1, C2, and C3. Now, putting the value of C0, C2, C1, C2, C3 in the particular equation that we have generated, that is PU. The PU was C3U3 plus C2U2 U square plus C1U plus C0. Right? You can put the values of C0, C1, C2, and C3 in this equation. If you put these values, say twice of P0 minus P1 plus P0 dash plus P1 dash into U3 UQ. This is the value of C3. Similarly, putting the value of C2 equal to this plus twice of P1 minus P0 minus twice of P0 dash minus P1 dash, and taking it in complete bracket into U square plus P0 dash U plus P0. This is how it should be written. So this equation is called Hermite cubic spline. So this equation is called Hermite cubic spline. You can rearrange the term according to separating P0, separating P1 dash and P0 dash. Similarly, you can segregate all these values and you can find the values in terms of U, U1, U square, UQ in terms of these values. This is your Hermite cubic spline. So this is the article that I want to print it on the board also. After this, what is to be done is now same equation that is there, twice of U cube minus 3U square plus 1. You can write it in this form also. 2 minus 3, 1. 2 minus 3. There is no term related to U. That is why there is a U in 0 over here. And this, we have U cube, U square. There should be a U over here. That is why we have put it 0 over here into 1. Again, we are writing this equation in the form of matrix. Then minus 2, 3, 0, 0. There is U cube, U square. There is no U and no constant term. So we are writing minus 2 and 3 and 0, 0 along with it. Minus 2 and 3, 0, 0 along with it. Then U cube, U square and U. There is no constant term. So 1, minus 2 and 1. 1, minus 2 and 1 and 0 along with it. Similarly, U cube and U, and there is no U and 1. So we are writing 1 and minus 1, 0, 0. So this is how you can write it in the matrix form. Right? So this is about Hermite cubic spline. These are some of the diagrams or some of the curves that is generated with the help of cubic spline. A random shape like this, or like this, or like this, can be generated with the help of cubic spline. It is only drawback that a Hermite cube spline has is it needs 2 points and 2 tangents also. You cannot control more than 2 points. If there are 3 points, you need to generate a curve related to 3 points. Then you cannot draw that curve with the help of Hermite cube. That is a big disadvantage of this Hermite cubic spline, and that was the initial starting of this cubic spline or curves. So this is some of the curves that are generated with the help of Hermite cubic spline. Some disadvantages of cubic spline. It requires a specification of tangents. This information is not always available. So as there is a requirement of 2 tangents also. So that tangents are not available all the time. So you have to calculate these values. So limited to 3-degree polynomial. Only 3-degree polynomial can be generated, or only 2 points can be used to generate a curve. Only 3-degree polynomial is there to generate a curve. So the curve with the higher degree of polynomial cannot be generated with the help of this Hermite cubes. Curve cannot be modified locally when a data point moves. The entire curve is affected, resulting in a global control. Now you can see this. If you want a curve to move from this end to this end, but you cannot do that unless and until you move this point to another point. The whole curve will be moved from one place to another. So localized means if you want to change a curve from say center, you want it to move downwards. This is not possible in this particular cube spline. Though the next curves that we are going to have is more flexible, they can be moved from any point and any place. So before moving to next curve, I would like to have a first poll for today's lecture. So moving on to next curve, Bezier curve. So there are three types of curve: Hermite cubic spline, Bezier curve, and B-spline curve. Right? Uh, Before moving to B-spline, we must understand what is a Bezier curve. And it was generated by some scientist whose name is Pierre Bezier from 1910 to 1999, Reynolds. So in 1962, French engineer P. Bezier, while working for Renault automobile manufacturer, developed a system of curves that combine the features of both interpolating and extrapolating polynomials. So it was designed by some French engineer whose name was Bezier, and he was working for Renault company, automobile company. You all may be aware about the Renault company that is producing Quid and all that, Duster. Developed a system of curves that combines the feature of both interpolating and extrapolating. So it was a curve that is combining the features of both interpolating and approximating polynomials. The Bezier curve represents the approximated curve. These curves are synthetic and can be joined together to form a very smooth curve. So it is an approximated curve and they can be joined together to form a very smooth curve. For data fitting and interpolating curves work best, whereas for free form geometry interpolation cannot be used and approximation becomes necessary. In many engineering applications, smoothness of the curve is preferred over the quality of interpolation. These curves are flexible and local changes in the shape do not affect the entire shape of the curve. That is the biggest advantage of Bezier curve. You can change the locally, right? Uh, Localized change of the shape can be done with the help of the Bezier curve. Though it is not that flexible, the most flexible one is the B-spline curve. You can see that the end control points lie on the curve. Rest the points they doesn't lie on the curve. The diagram that is at the bottom of the screen. That's why we call it. It is combination of interpolating and extrapolating, right? Approximation. In first case, the point should be on the curve, and the second case, it should be outside the curve. So it is combining the both the vectors of these. The end points are on the curve, and these points are not on the curve, and still they are controlling the curve. The shape of the curve is controlled by a set of data points. These data points are controlling the shape of the curve. If you change the shape from, if you pick that P1 from this point and reaches there, this curve will be sharpened from this end, like this. Tangent first derivatives are not used in curve development. There is no tangent in this particular curve, as there is a requirement of curve tangent in Hermite cubic spline. There is no requirement of any tangent. The order or degree of Bezier curve is variable and set to a number of points defining it. It can be 3 degree, 4 degree, 5 degree, 6 degree, depends upon the curve, how many points are there, control points are there to generate a curve. Only the first and the last control point actually lie on the curve. As I told you, only first and the last point lie on the curve. Rest the points, those are inside the curve, they are lying on outside the curve. They may be on the left, on the top, or on the bottom, or left on the right, not on the curve. Other vertices define the order and derivative and shape of the curve. The curve is also tangent to the first and last polygon segment. Now the curve that is being generated is tangent of the first point and the last point. This polynomial you must remember. This has to be remembered. Bezier curve for n plus 1 control point can be defined by the following polynomial of degree. So you have to just remember this and putting the values from I equal to 0 to n. There can be n points in this Bezier curve. Suppose it is a 5 point, so n will be 5. You have to generate the polynomial putting 0 to 5. Similarly, whereas PU is any point on the curve and PA are the control points, then the Bernstein polynomial given by. So there is again another polynomial that is given by Bernstein. So that is this one. Similarly, C are the binomial coefficient given by. That can be, if you want to solve this, that is equal to n factorial, I factorial, n minus I factorial. So this is how it is generated. You can use this. Just remember this first polynomial. That is important. It is observed that Cn comma 0 is Cnn is equal to 1. Right? The first and the last point, they are equal to 1 in this Bezier curve. Cn comma 0, that is the first point, and Cn comma n is the last point. They are equal to 1 in this polynomial. Equation 12 can be expanded using equation 13 and 14 as follows. You can expand this equation equal to this, like this. Similarly, for n equal to 3, you can expand it like this. And this is the generated polynomial, the Hermite cubic spline. This is the same equation that is Hermite cubic spline has been given. This equation is similar to that. If you solve this, we have put a value of n equal to 3. You are given this polynomial. If you solve this polynomial, this is equal to this, and this polynomial is very much similar to the polynomial that is being generated with the help of Hermite cubic spline. In matrix form, it can be written as P0, P1, P2, P3. So P0 is when u equal to 0, 1, 2, 3, and it can be written like this. The same equation. This u3, u square, u1. And this. These equations you have to remember. This is, as I have told you earlier also, this is the most difficult part of history. And many things that are we crammed in it. So these are the curves that are being generated with the help of Bezier curve. So 2 points, first and the last point lie on the curve, rest all points does not lie on the curve. This is an example of again Bezier curve. There are 3 points and 2 points lie outside. Similarly, these 2 points also lie outside. These 3 points lie outside. First and last are the common points. In this, it is a 5-pointer. Now 6-pointer. In fact, 4 points lie outside the curve to generate a circle. So these are some of the examples of Bezier curve. Some of the characteristics of Bezier curve again. The curve interpolates the first and the last control point and approximates to the other point. So the first observation is that only the first and the last point lie on the curve. Rest all other points lie outside the curve. That is the definition of that particular is, or you can say a technical term for that is the first point and last point is interpolates and rest are explorating, approximating. This is already I have explained in very first and second slide of this chapter that what is interpolation and what is approximation. So interpolation is the points those lie on the curve and the approximate is when the point lie outside the curve. The curve is tangent to the first and the last segment of the characteristic polygon. When you have generated a polygon, the first point and the last point of the polygon are the tangent of the curve. The curve is a tangent of that. The curve is tangent of that. And third point, the curve defined by the given n+1 control point lies completely on the convex hull of the given control points. The curve should be covered completely in the convex hull. Convex hull is the points that are there. The point should lie, the curve should lie inside this convex hull. So this is the convex hull from P0, P1, P2. This is the convex hull and the curve is lying inside. If you join this, so that means the curve should be inside the convex hull. Convex hull is the points that is there. If you close those points, that particular closed figure is called convex hull. And in this particular case, all the whole curve should be inside that convex hull. You can see all the curves are inside the control points. If you generate a box, it is already generated a box. If you connect P0 to P3, this is curve is inside that. If you connect this to this, again this is inside the convex hull. The curve is symmetric with respect to u and 1 minus. This means that the sequence of control point defining the curve can be reversed without change of the curve. You can change the sequence of control points also. The closed Bezier curve can simply be generated by closing the characteristic polygon or by closing P0 and P0 to coincide. So as in the last two figures, you can join the first point and the last point to generate a closed figure. This is what the last point is stating. The interpolation polynomial BINU has a maximum value of this Cn, I, I divided by n is for I, 1 minus I by n minus I, occurring at u equal to I by n, which can be obtained from the Q. This implies that each control point is more influential on the curve shape at u equal to I. So this states that the control points are most influential at u equal to I by n. For example, for cubic Bezier curve, P0, P1, P2, P3 are most influential when u equal to 0, 1 by 3, 2 by 3, and 1 respectively. When it is in a fraction, it is giving the best results, most influential. The curve shape can be changed by moving the position of the control point. Just see the diagram that I was trying to explain you. This is the curve, the initial curve. If you want to change the shape of the curve to this end, like this, what is to be done is pick this point and drag it to this end, and that curve will be shifted like this. There is that particular thing is called localized change of the shape. That is not possible in case of Hermite cubic spline. So some of the disadvantages of Bezier curve. The degree of the Bezier curve depends on the number of control points, right? In case of Bezier curve, the degree depends on the number of control points. It is one more than the control point. More number of control point means higher degree of curve, which means more computational effort and time. As we have already seen that computation is very if you want to compute the degree of polynomial, it is very difficult as you have to put as the number of control points increases, the degree of polynomial also increases. So this is an biggest disadvantage. You need to calculate more if it is having more control points. Bezier curves lacks local control on the shape modification of the curve, though it is providing us, but still it is not that flexible. Bezier curve, the shape can be changed using multiple control points, but more computational effort is required. You can change the shape using multiple control points, but as you increase the number of control points, its computational effort is increased. You need to compute more to increase the better shape of the curve. So this is the sum of the disadvantage. Basic disadvantages: more computational effort is required. There is though there is a localized change is possible, but it is not that flexible as compared to B-spline curve. So let us move to the last curve, B-spline. Before moving to the B-spline curve, let me take the third pole. So next is B-spline curve. So as we have done two curves out of three, Hermite cubic spline and Bezier curve. Now we are on to B-spline curve. These spline curves were developed to overcome the limitations of Bezier curve. Some of the limitations that are there. Know that the flexibility of the curve is not that great, and the computational effort is required in case of Bezier curve was quite high. Those limitations were overcome in this B-spline curve. B-spline curves are the proper and powerful generation of the Bezier curve, though they are also called Bezier curves. But it has powerful generation of Bezier curve with little computation. They provide local control of the curve. These provide the ability to add control point without increasing the degree of the curve. In case of Bezier curve, the control points can be increased till the degree of the curve may be same. These provide the ability to interpolate or approximate a set of given data points. They again provide you the flexibility to interpolate and approximate the set of given data points. Wherever you want to keep the point outside, wherever you want to keep the point on the curve. Depends on that. Now the polynomial on which this curve is in, or this equation of this particular curve is generated is this. For a polynomial, the equation is so given n plus control point T0, T1, Tn, a B-spline curve of the degree k minus 1 defined by these control points is given by sigma I equal to 0 to n T is equal to I and n I comma k to u. This is the equation for B-spline curve. Pu is any point on the curve and Pi is the control point. Pu is any point on the curve, you can take any point on the curve, and Pi is the control point which controls the shape of the curve. Whether you take the point up and down, it depends on Pi to control the point. And IKU are the B-spline function. The parameter k controls the degree of the curve. The range of u is not 0 to 1, but it varies from with the number of control points and degree of. So the value of u is not dependent on or not is not from 0 to 1. It depends on the number of control points and the degree of the curve. Some of the characteristics of the B-spline curve. It is very flexible curve, as it is clearly visible on your screen that let us see this. This is the initial curve, the center one. If you take this P3, to P dash. This is P star. The curve, instead of moving this point, it will move like this. And similarly, if you take that point, instead of moving towards upper side, if you move the point to the lower side, suppose a point, instead of point moving to up, it moves to P3 double dash or P3 double star. Now the curve which was being moved from this to this, it will move like this. This is localized control of the shape of the curve. Now, just see the board. I will show you the how to basically how it is flexible. I have drawn a curve. Let us take P naught, then P1, and then take P2, P3, P4, P5. These are the control points of this particular. And if you want that curve should move like this, instead of it is passing through this point, instead of this, we want a sharp curve passing through this. What is to be done is pick this point up and take it to this P3 star or dash. Now the curve will become like this. Similarly, if you want this curve, instead of moving to the top side, it moves to the downward lower side like this. It is a curve in the lower side. That will become, it will become only when you bring that control point to this point. This is the localized change of the curve. This is localized change of the curve. I hope you understood this. So the local control of the curve can be achieved by changing the position of control points. I hope you understood what is control point. What we are talking about this control point, right? So non-periodic B-spline curve passes through the first and the last control point P naught and Pn and is tangent to the first and the Pn plus one and minus n segment of the control point. So basically, it is the tangent of the first and the last. Rest all the points lie outside the curve. Increasing the degree of curve tighten its illustratively. As you keep on increasing the number of points, controlling points, the the desired curve can be generated with the help of that. A particular shape can be achieved by increasing the number of control points. Lesser the degree, the closer the curve gets to the control point. For k is equal to 1 at 0 degree curve results in curve itself becomes control point. For k equal to 2, curve becomes polygon segment. A second degree curve is always tangent to the midpoint of all the internal polygons. It's not the case for that. And if k is equal to n plus 1 control point, then the resulting B-spline curve becomes Bezier curve. In this case, the range of u becomes 0 to 1. A B-spline curve is contained in the convex hull of control column. Basically, again, a curve generated in case of B-spline is also contained inside a convex hull, generating uh, the curve, the control points of the generating curve. Multiple control point induces region of high curvature of the spline. This is useful when creating sharp corners in the curve. The effect is equivalent to saying that curve is pulled more towards the control point by increasing its multiplicity. So next part, this is all about curve. Now next part is curve surfaces. Now next part is, this is all about B-spline curve. We are done with the curve. This is just a 2D curve. When you move to the 3D figure, so that is generation of curve. Now we are to study about the need for the surface model. The wireframe models are unable to represent complex surfaces of the system like car, ship, house, airplane, wings, and castles. So we are not able to show the shape of the car, surface of some ship, airplanes, and all that. For that, we need to generate some surface. Surface modeling is a widely used modeling technique in which objects are defined by their bonding. Surface model can be used for calculating mass properties, interference between parts, for generating cross-section, FEM, and integration. This is already, we have studied about this also, that to calculate mass properties and interference, we need to generate its surface. Surface models are more complete and less ambiguous, representation that wireframe model. Now, the confusion that is being there when you are working in wireframe model, that is being eliminated in case of surface model. There is always a confusion that which face is the front one, which is the rear one, and which line, which point is to pick when you are creating something on it. If you are on the surface, you are clearly visible that this is the surface, this is the front surface, this is the rear surface in this case. The representation of curve surfaces, it is just an extension of representation of curve. Just like we have represented curves, we can extend that curve into surface. We can represent a surface as a series of these points inside the bounding space. So surface can be two-dimensional space or in three-dimensional space. So it can be two-dimensional also, it can be three-dimensional also. Surface can be described using non-parametric and parametric equations. Similarly, as we have studied about parametric equations and non-parametric equations, just like surfaces, like circle, point, line, left, and there are some non-parametric equations and parametric equations. Non-parametric, implicit and explicit. We have studied about them. So same thing can be done. Same equations can be used to generate a surface also. Surface can be represented by equations to pass through all the data points or have patches of them connected as the data points. So just the extension of what we have studied about surfaces or curves. Analytical surfaces, plane surface, ruled surface, surface of revolution, and tabulated surface. In case of analytical surfaces, as we all know, when you are working in machine drawing, you all have studied about plane surfaces, ruled surfaces, surface of revolution, and tabulated surface. Plane surfaces are surface if you pick a rectangular sheet and join it end to end, that the surface that is generated by that or this particular surface is called plane surface. And sorry, that plane surface is a sheet of rectangle shape, and if you join that particular sheet from end to end, it will form a cylinder, and that particular sheet will become a ruled surface. And surface of revolution, just wait a minute. That is that is called a ruled surface and surface of revolution. Sometimes you generate a triangle and fixing at one end to generate a cone. It is called surface of revolution. Similarly, tabulated surfaces there. Synthetic surfaces are if you use a hermetic curve and then expand it to form a surface, it will be hermetic bicubic surface. If you use Bezier curve to generate a curve, then extend it to form a surface, it will be called as Bezier surface. B spline, if you are using B spline surface. Similarly, cone surface are there. That is not in your syllabus. So application modeling part in CAD can represent representation of data surfaces like isothermal planes, stress surfaces, and contours. So if you need to show the surfaces and stress the surfaces and some modeling process, you can use this. So again, it is a non-parametric, as we have already studied about this non-parametric equation when x, y and z are dependent on x and y. Yeah, similarly, in the case of this non-parametric curves, non-parametric representation of surfaces also, y, x, y and z are dependent on x. As you can see this, x, y and z are there, three coordinates, where y and z, where y is a function of xy or y is a function of z x and z is a function of x. Similarly, that can be in 2 points also, implicit and explicit. Natural choice effect is polynomial. Thus, for analytical representation of surface, we can use equation of a type like this. Now, parametric representation is more and precise. Parametric surface patches are not individual. Normally, many parametric surfaces in parametric equation we use third variable as to show the rest of the three coordinates. One is the same. One is the same. So parametric surface, as in case of we have already studied that if x, y, and z are dependent on some third variable, fourth variable u, then it is called parametric equation. So normally many parametric surface patches are joined together side by side. In this, you can see this number of patches are formed. This is formed with the help of some curve. This is formed. Then they are joined together to form a particular surface. So some of the analytical surfaces that are generated. This is the ruled surface. This is plane surface or rectangular surface, tabulated surface, and this is a solid of revolution. In case of we generate this surface, then rotate it to form this particular surface, Bezier surface and B spline surface. So this is all about surfaces or curves and surfaces. This is the last slide of this lecture. If you have some question, you can ask me. We will again meet in the evening also. I am going to